Oh, really? When you just got here? Is that what you're saying?
Yeah, like I got home. That was
If you really want to bond with your potential client, there he is.
Make sure it's streaming.
Oh yeah. Good on. It was good, man.
I'm not doing a camera on this. Yeah, it's that like conscious one.
Yeah, there's some.
April. I always forget that.
It's super delayed.
Yeah, it's like 30-second delay.
Is it? Okay.
As long as it's consistent.
Yeah, I think I
On TV, it's like 3 seconds.
I think I put a longer delay so it doesn't buffer, and I can't change it anymore.
On the YouTube there. Twitch stream literally several people. You should have Twitch stream and said something like World of Warcraft. Heavy finale. Never boss.
Give them some. You get the instruments. You won't believe it. It's incredible. Computer science and stuff like
That's like the school.
genetics was so. It's like the classes start 10 after, so like professors treat
Yeah.
Hey,
What the heck is that? That's awesome.
it's a mic.
Yeah.
So I'm live streaming, so Austin mentioned he might shoot you text if you have a question, but otherwise I can see people's comments.
We should have had him on the committee. Awesome. You all set? Anything, any story I shouldn't tell as I introduce you?
I thought we weren't doing that. That is now the video where Austin releases the karaoke.
Exactly.
How are you?
Good.
Excited? That's a microphone.
Is it?
So I'm doing like a YouTube live stream to.
Is that yours?
I have like some family and friends who are out of town. Like my parents.
And I really have to do that.
I'll turn it off for the closed doors.
That's a really great question. Well, everything is done. As the studies are done, every study's been published, it's all published. I'm presenting it all in the next 2 weeks. The problem now is just writing the dissertation. I thought it would be possible to get that written by December. People's not so sure that that's possible. So she wants me to push it off until spring. So I guess spring. I'm really shooting for December. I'm ready too.
You didn't hear Jody say something like you can't come, did you?
I know. And I saw what Ghazi went through. He rewrote his dissertation at least 3 times, so I know to expect the same from me. So I'm trying to set my expectations that, like, I really feel like, given that it's all published and everything, I should be able to get this done by December. There's no reason not to. But I did take a break this summer. I taught classes instead, so I can do teaching evaluations, so I can use those for my job applications. So classes finished last week,
307?
and now I'm doing a presentation.
Well, Charger doesn't do anything with signal.
But only the job application will be too bad.
And Brian,
teaching
he's
faculty that's brought me on.
he sent me something about parking.
I went to 6 months.
Do you have locker?
You're graduating here. So job market's really good.
No parking? Was there no like?
Job.
Is today moving day? Like there's no. So I sent him to the Duck parking garage because that's usually the easiest.
Oh,
So
Brian
emailed me,
Clare?
yeah, he emailed me no parking. I've got to look off campus. Be there as soon as I can.
Oh dear. Okay. Yeah, I don't know. Classes start.
I think so first. I think I want to try the teaching.
Yeah.
That was always my goal.
But it might be orientation.
If it doesn't work
today,
out,
like
well,
parent
then
orientation.
Joe Sullivan.
Alright, well it's till 10 after, right? So
Okay. Okay.
The deadlines for the teaching oriented faculty ones are surprisingly very early. So far, one of the books has gone out earliest I have is October 30th. Most of them are around there. I did this last year when I thought I was graduating, so like I built the spreadsheet of everything.
We're gonna get wet.
Thunder.
We'll see.
No, I meant if there's thunder. You're in left.
Left and side
We
here.
got the prime seats.
I get to sign first.
Just one more committee member. Trying to find parking. Brian Clare.
Is that the external guy? Yeah, I say guy, but that's Brian for that.
It's a little bit more ambiguous than it used to be.
That's why I have like better correct myself.
Yeah, he's a full member with us.
Get the park and then find the rules later.
Yeah, Michelle ran user studies this summer. They had to park in that garage over there, and getting the people through that construction back here was so hard for her. Phone calls, like, yeah, we know. I know you will.
Especially once you go to like what side, you don't see like the buildings. Even
I
if
know.
the sign is not maybe the right place. So you should be able to come.
Yeah. The view got pretty nicely compared to St. Louis, and then put it all back. So I'm kind of curious if they'll clean it up again for the school year. I hope so. It's chemistry.
Just like not engineer.
No, it's under that bridge over Forest Park Parkway next to us. We're gonna put in a new bridge.
To the fourth floor.
Oh, not Forest Park, I mean to the left. Yeah, sorry.
So when I was
Oh, really?
I mean, it's not hurting or anything, it's just like, every night I'm so tired, I just wanna like, and then I have to like, get my mattress off, it's just, 'cause I don't like it.
Well, if you saw their big master plan, they're gonna do what they did to Brian and John's.
I could, I could just pass it, but then my mom would be like,
I can't believe how much.
I know.
Actually, I can do it.
Oh, I don't even know.
My live stream.
It looks like it's a lot. Because they're gonna do Dylan after they finish Brian, and then eventually they'll kick us out. Well, I mean, I'll be gone, just kick you all out. Because like it's just one of the new buildings. Like daydream or whatever. Like, I don't know, 10 years or something, right? I don't know how many years dream.
So you still practice.
This is
I'm
not.
supposed to start that big underground parking garage thing next summer. So I guess, so that was taking like 2 years, so just presentations.
Oh, and
if it offers that, that's like
I'm really over that. We've only dealt with it for like, what, half a year? you're right. It's not going to end anytime soon.
That's so
No,
that
just, well,
since
just
we're
for
going
some background, not really good, gift money.
That's alright.
But someone in your production, I helped them. So this both is just sort of the modeling. Really realizing how to yes, my student is leading the team, really hiring PhD, communication, competition photography, machine learning people. No, from
I mean, face
company invests in business. It's really Seattle downtown. It's really one block from fish market. It's a crazy place.
and it's hard for parties.
Yes, yes. It's really second class.
No whiteboard in here? Are the walls whiteboard?
10 floors.
No, it's not.
Got some paper.
Is there a whiteboard behind
Just
that?
all huddled together.
I just for some reason this is the renovation. So there's
You know the biggest
Yeah,
is there a whiteboard behind that?
I don't think so.
no.
Yeah, it's a shame.
I
I didn't even think about that.
Just around seats for I don't know where it's photographed.
Well, then you might as well use permanent marker right on the walls.
Somebody they somehow just automate the procedure. But not that tedious. Something we are all by the manager. And we do processing
Can we start with four committee members if one of them is on his way to trying to park?
trying to figure out
Plenty of fun.
So I think he said he went to the duck. Is that like orientation day?
Yeah, it is orientation.
Yeah,
Not
actually,
here.
yeah. But you also count as an external member. Like, so you're not.
We have new rules.
I'm the 5 years ago.
I'm the new head of the graduate committee in ESE, so I should know this.
She was like on a vision.
I was like in my place.
And I think it's that close enough.
It's about developing some motivating people to make the minds of getting there.
I'm thinking about like a dress code or something
For your party? Exactly. Wait, for your party?
I don't really love doing this.
Yeah, the way you kind of
like there's up with kind of strange.
That's a lot.
Nice video. The motivation for sellers.
But I'm afraid if we don't go to the photo shoot, next time I'm so good.
I'm gonna dress up. Wait, come on. We're gonna dress up anyway.
Yeah, we're gonna.
No, the dress code is starting and pretty soon.
No.
Like sleeping.
Can I just wear a jeans?
Oh,
Yeah.
Like, is there any time I want if we can cancel a photo? We'll have energy.
That's what?
I love just hanging out. You're like,
I'm just kidding. I mean, you guys have.
I'm reading the game.
Yeah, I know.
Well, this time in Taiwan,
What other
Detailing anything about this
But they make it
ground.
committee.
Facebook group, I got like the map, details, construction.
I'll tell you, those maps are.
Oh, really?
We fought for those for years on the user studies. Yeah, I mean, like, just over and over and over again. You know, it works constantly. Tell them to, like, no matter where you are, look for the smokestack and go to it. It's amazing how well it works. Everything else, the users, like, they get lost. They end up at, like, the damn fourth garage. Or, like, how did you end up on that side of campus?
Yeah, especially this building, it's like, there's no front.
No.
It's a courtyard.
No, so the way that we did it was like find this, and then Jolly used to have this big
Sorry.
yellow fire hydrant. And I say, look for the fire hydrant, that's the entrance.
Good morning, everybody. It is my great pleasure to introduce Ian Schillebeeckx, who is going to be getting his PhD defense. This is an official exam of Washington University, so if you haven't been to one of these before, the process is that Ian's going to give a talk. There may be questions during the talk. At the end of the official talk, there will be questions from the general audience, after which they'll be invited to leave, and there will be a closed session with the committee. So with that structure of this event, I would like to formally present to Ian.
Thanks, Robert. Thanks, everyone who came out. It's certainly inspiring to see everyone's smiling faces. Just a quick disclaimer, so this department tends to be more precautious for digital privacy, so I wanted to remind everyone that I'm actually live streaming this presentation and recording the audio with this mic, but I'll only be streaming the presentation itself, so if that bothers anyone, we can not do that. But now the disclaimer is finished. Yeah, welcome. Thank you, guys. I'll be presenting my dissertation where we do geometric inference with lenticular arrays. So understanding 3D position is really important for tasks like measurement, navigation, and for applications like automated manufacturing. And visual sensors like cameras are useful ways to measure and describe the world, but they require geometric inference in order to understand 3D location. So here are some examples where a camera in this robotic arm allows it to identify, locate, and grasp this tray of poker chips. And another example is shown here on the right where a video that locates these balls that are on this surgical tool enable image-guided surgery. So the required geometric inference necessary to understand where 3D points are begin by finding known 3D points in the image. And to simplify this, these 3D points are typically made easy to find. These easy to find points are called fiducial markers. So here we show an example on the right, which is the chessboard, where the 3D points of the corners of each square are known. The fiducial markers are the standard for a lot of applications in computer vision. For example, for understanding where an object is relative to the camera, which is called pose estimation, or understanding how the camera itself captures the world, which is called camera calibration. And fiducial markers enable these two tasks because of the way that they create relationships. So in particular, they create a relationship between the known 3D location on the fiducial marker and where that point projects in the image. And so this relationship between the 3D and the 2D point is called a point correspondence. And sometimes this visual cue can be limiting because positional constraints are combined to create orientation constraints. So with an example, we consider two images of 2 points on a plane that's nearly perpendicular to the camera. In the two images of these 2 points, they'll look very similar, and this creates an ambiguity in inferring the actual 3D orientation of the plane. So as an example, and so as actually the plane becomes closer to this perpendicular position, we see that the estimation error of the orientation actually increases. So this dissertation considers an alternative fiducial marker design. Here we introduce fiducial markers that give orientation constraints in addition to positional constraints. And these fiducial markers are created from microlens arrays, and we show an example here in this video where we rotate the fiducial marker by 1 degree in every frame. So easier geometric inference is possible with these type of fiducial markers because they create orientation-specific appearances. So we create these fiducial markers using 2 types of microlens arrays, and these differ in the shape of the elements that comprise the array. On the left, we show one of them, which is a lenticular array, which has optical elements that are cylindrical. And this array can be designed such that it creates different appearances for rotation around a single axis. The 2D analog to this is the lenslet array, which has spherical optical elements. And this array can be designed such that it creates different appearances for viewpoints that change in spherical coordinates. So in this dissertation, we use these 2 types of microlens arrays for geometric inference, and we present 4 contributions. In the first, we show how to encode orientation using colorful lenticular arrays. We use small versions of these to do pose estimation. And thirdly, we use large versions of these colorful lenticular arrays to do camera calibration. And finally, we created a different type of fiducial marker that has black and white appearances, and we use these for pose estimation. And I don't think I mentioned it, but this last contribution uses the lenslet array in contrast to the lenticular array. So to frame these contributions, I want to go quickly over some existing fiducial markers that are related. So a fiducial marker is an object that a camera recognizes in an image to relate the world to an image. The traditional designs have black and white patterns like this chessboard. And these patterns have high contrasting edges and corners, which not only make it very easy to find in an image, but also enables systems to measure subpixel accuracy locations in an image. So these traditional black and white fiducial markers might vary by the type of symbols or codes that they have inside of them, which allows 2 or more fiducial markers to be able to be identified in a single image. There's also been some work on creating fiducial markers whose relative appearance depends on orientation. One example is the Agam fiducial marker, which is inspired by Yaakov Agam's artwork. In this artwork, a single piece actually has 2 or 3 different appearances for different viewpoints. The fiducial marker itself is comprised of many rows of triangular prisms, such that one side of each prism is black, while the other is white. So from far away, depending on how gray it is, you'll know what orientation you're viewing the fiducial marker. Another example is the MIT bow code, which creates a light barcode that is structured to be seen by an out-of-focus camera. So here's that fiducial marker shown with the naked eye, and as you defocus the camera, you can actually start to resolve the barcodes of the marker. For different orientations, you'll actually see different QR codes. So there has also been work using lenslet arrays to create a light field probe. This light field probe encodes both the origin and the direction of light rays using color. And the authors of this light field probe use it to observe how light rays bend through transparent objects. By observing this interaction, they're actually able to reconstruct the 3D geometry of this transparent object. Most related to our work is the lentimark and the array mark, which use the 2 same type of microlens arrays that we use. The microlens here create orientation-specific appearances that manifest as a black bar or a black cross that translates relative to the rest of the marker. By adding these microlens arrays to traditional fiducial markers, they're able to improve on pose estimation accuracy. However, like traditional fiducial markers, the lentimark and array mark give cues from the relative location of these landmarks relative to the rest of the marker. And this affects accuracy when the visible size of this marker gets small in an image. In contrast, we create fiducial markers that give orientation cues from color. And so no matter how small it is, we can still observe a single color, and this gives us strong orientation constraints. So now I'm going to get into the meat of the talk. Something I mentioned, forgot to mention earlier, is that I'll be focusing a lot of the talk on these last two contributions since they were done after proposal, but I'll still go briefly through the first two. And so we'll start with the first one where we create and design lenticular arrays that encode orientation using color. So to make it easier to talk about these lenticular arrays, I first want to introduce some terminology. So the lenticular arrays themselves can be oriented along an axis that is parallel to the cylindrical elements. And we call this direction the major axis. Perpendicular to this and the surface normal is the minor axis. Traditionally, the individual elements of the lenticular array are actually called lenticles. So in this slide, we show a cross-section of how the lenticular array creates orientation-specific appearances. So what happens is that each lenslet of the array focuses parallel rays of light onto a pattern adhered to the back of the lenticular array. Therefore, for different orientations of parallel light, the lenslets array will actually focus onto different colors. Therefore, for different orientations, the lenticular array itself will appear to have that color. So as the examples I show here on the slide, if you look at the lenticular array from front to parallel or perpendicular, it might look magenta, but as you rotate it, it might look blue or teal even. So these lenticular arrays that we design change color when rotated around the major axis. And here we show a video of one of those lenticular arrays on a motor, rotating every frame around the major axis. So these lenticular arrays create a very strong relationship between the angle rotated and the hue that's observed. And we show this relationship here on the left. We term this relationship the hue response function. For a set of viewpoints, this is a one-to-one relationship between the observed hue and the angle rotated. So if you'd like to infer the hue, so this enables one to infer the hue from a known angle rotated, or vice versa, infer the angle rotated from an observed hue. So what makes the lenticular array useful for inference is that it constrains the direction of a viewer viewing the lenticular array. That is because any ray that views this lenticular array that is perpendicular to the end hue and lies on the plane defined by end hue will see the same color appearance, so the hue. So with a known HRF, an observed hue, we can actually infer the direction of this end hue, and therefore use the lenticular array for geometric inference. So now I show how we can use these colorful lenticular arrays for pose estimation. So the pose estimation problem, we seek to define the relative rotation and translation that relates the reference frames of the camera and some object. And we do this using small lenticular arrays called chroma-coded markers. We place these markers at locations C1 and C2. So then by taking an image of this object with the markers on it, we can use the measured hue and the position of the markers in order to estimate the rotation translation to understand where the object is relative to the camera. To do this, we choose to model a pinhole camera viewing the lenticular array. In this model, a pixel P views array R according to some matrix K. This K is called the camera matrix, and it's typically found with camera calibration. In this chapter, we assume that it is known. So when a camera views a lenticular array, we can relate the reference frames of those two objects via rotation. More specifically, when a camera observes a particular hue along a ray, we know that that ray must be perpendicular to a specific end hue. For example, if this ray is red, then we know it must be perpendicular to the end hue corresponding to a red hue. Rotating this lenticular array into the reference frame of the camera, we can derive a constraint with a dot product, which we show here at the bottom. And this is called the lenticular constraint. This is interesting for two different reasons. One, it's a very simple mathematical relationship. And second, it only depends on the rotation. So it does not depend on the relative position or translation of the lenticular array in reference to the camera. With a second chroma-coded marker, we can derive another rotation constraint. And in this constraint depends on the relative directions of the two markers observed in an image. So with these two constraints on rotation as an objective function, we can estimate the rotation of an object with two or more markers. We parameterize this optimization, specifically we parameterize the rotation by the Rodriguez parameters. And we'll note, because we use the lenticular constraint as the objective function, this is decoupled from translation. And in experiments, we observed that it converges actually very quickly. Now, to optimize for translation, we can derive a constraint on translation per marker. And this constraint depends on the relative direction of each marker observed in the image. With one equation per marker and the previously optimized rotation, then we have the necessary constraints to optimize for the translation with this nonlinear objective function. So I quantify a lot of the results in the dissertation, but in this presentation, I'm only going to show you an application of pose estimation using these chroma-coded markers. In this application, which I'll show as the video, we use two different chroma-coded markers mounted on the end of this pen in order to actually track what is being written on a piece of paper. So in this video, I'll show you the top, which is the raw frames. On the bottom left, this is a side view. And what you'll see is these blue points represent the 3D position inferred of the markers. And because we know the length of the pen and the orientation of the pen, we can actually infer what the 3D position is of the end of the pen, which is writing on the piece of paper. And you'll see those points as red points here. I show another side view, which is a view that is parallel with the piece of paper. So here I'll go ahead and show the video. In real time, you'll see the estimations on the bottom. You can see, because with our markers we get really great rotation estimation results, that it's pretty easy to infer what is being written on the piece of paper. Whereas if you just looked at the raw 3D positions of the markers themselves, that might not be as apparent. In addition, when looking from a side view parallel to the camera, you'll notice that unless the pen is being lifted up in between letters, all the points of the end of the pen are coplanar, which makes sense because we're writing on a piece of paper. So that's how we used small lenticular arrays called chroma-coded markers for pose estimation. Now I'll get into some of the, take a deeper dive into how we use large colorful lenticular arrays for camera calibration. So lenticular arrays can be used for camera calibration because of the way they look for cameras of different focal lengths. In this slide, we consider a very large lenticular array that takes up the entire image of a pinhole camera. On the left, we show a pinhole camera that has a very long focal length. In this situation, all the rays viewed in the lenticular array are almost parallel, and so they'll see the image from this camera will be almost all the same color. In contrast with a pinhole camera with a very short focal length, because the incident angle of the rays viewed in the lenticular array are quite different, they'll see many different colors. This relationship between the difference of color seen in an image and the focal length are what inspire this chapter. To do this calibration, we create a calibration object using large lenticular arrays. We use 3 of them such that the 2 flanking arrays are perpendicular in orientation to the array in the center, and we denote the orientation by these blue arrows. Here we show again 2 images, one with on the left of a long focal length, where on the right we see a short focal length image. What you notice is that these confirm the predictions we made from the previous slide. In particular, the long focal length image sees nearly the same colors across the entire array, while the short focal length image sees many different colors across the lenticular array. And so to do camera calibration, as before, we choose to model the camera as a pinhole camera. With this model, pixel P images array R according to a camera matrix K. Now the camera matrix K typically has 5 degrees of freedom, but in our case, we simplify it to have a single focal length. We decide that the skew is 0, and we assume that the principal point is the center of an image. And so in this chapter, what we're doing is we're taking an image of this calibration object in order to understand what K is. To do this, we derive a modified version of the lenticular constraint. To do this, we observe the ray R to make the constraint in terms of the matrix K. Then we can do some rearrangement by putting it in a matrix form in order to collect the unknown rotation and camera matrix K. Now, what's interesting about this constraint is that it doesn't actually depend on precisely measuring a point correspondence in the image. So what this means is that every pixel that we see of the camera calibration object can actually give a constraint on the rotation and the camera matrix K. So using this updated lenticular constraint, we can solve for K and R simultaneously. We don't optimize over the entire matrix K, but rather parameterize it by F and solve for only the focal length. This objective function, again, optimizes over the lenticular constraints derived from all the pixels imaging this lenticular array, so even with a small image, you might have thousands of constraints. Similar to pose estimation, this optimization is decoupled from translation. So here we show some results using this optimization. I show the raw images with the rotation estimation visualized as the directions of the local reference frame. In addition, in the title, I include the known focal length and the estimated focal length. What we can see is for images with a very short focal length, we get reasonable focal length estimations. However, we generally see about, in the best case, a 10% error. However, for medium focal lengths or even long focal lengths, we see very bad focal length estimations, which you might not expect in a dissertation talk. But what we found when trying to debug this was that actually this assumption where we assumed that there was a consistent relationship between the hue and the angle across the entire array wasn't actually true. Specifically, here's an example on the left of an image of the calibration object at a very long focal length. Again, because the rays that view it are nearly parallel, we would anticipate that the array would have the same color across. But as you can see, you actually can see it's much darker orange here on the right versus on the left, which is a more yellowish orange. And if you were to look at these two sides over a set of viewpoints, then what would you actually see the HRF at these points, that although they're the similar shape, they're actually quite different. And so this is why we had large focal length estimation error previously. And so the reason we have this changing relationship is because of a manufacturing challenge in creating lenticular arrays. The manufacture process involves printing a pattern such that each lenslet has all the colors underneath it. However, in creating the pattern, if there's a mismatch between the number of colors and the lenslets, then what we see is that there is a change in appearance for the lenslets of a different color. And so here's what it's supposed to look like on the right, where for the same orientation, all the lenslets will focus on the same color, in this case green. However, if this pattern even stretches by a little bit, then you'll see that for the same viewpoint, it'll actually focus on different colors. So on the right side, it's yellow. So for the image on the left, where we see actually three distinct colors, about green, blue, and maybe like a purplish, this results from a pattern that only stretches by 0.1%. And so it's really hard to avoid this, and in fact, even the professionally created lenticular arrays that we had made suffer from this manufacturing challenge. So to address this, what we do is we actually calibrate an HRF for many points across the lenticular array. To do this, we take our input image and we detect the corners of the lenticular array. Then using these corners, we can warp the image into a canonical view. And in this canonical view, we can sample the hue across across a grid across the lenticular array. And on the right, we show the hue measurements for that image. And this is a similarly far focal length image, and you can still see the manufacturing error that manifests. However, we use this procedure in order to calibrate many HRFs to have the relationship between the hue and the incident angle at each individual point on the lenticular array. With this procedure, we can update the rotation and focal length optimization. So now, instead of looking up the direction of the end hue using one HRF for the entire lenticular array, we can actually look up the end hue direction using the HRF and hue measurement at each grid point. Correspondingly, we also use the pixel position of each grid point as well. So with this optimization, we can get a better initial estimation on the rotation and focal length. So actually, to actually measure these hues that we used for the previous optimization, we end up having to measure these corner locations anyways. So we propose using the information, these pixel positions, in a second refinement optimization. So in this optimization, what we're doing is we're minimizing the reprojection error of the hue at those grid locations, but also the pixel location of these lenticular array corners. Later, we'll show the results of this optimization in comparison to the initial optimization showed in the previous slide. Yeah, absolutely.
With the direction of the major line axis, not the opposite, between the one in the middle patch, the two side patches. So there are two options, either horizontal, vertical, horizontal, the other way around.
Yeah.
I thought that there's a pros and cons. Which one? For the middle one, I thought is the opposite of what you are using. This is right now horizontal, vertical, horizontal.
Yeah, so you mean,
Cylinders are.
so this is like, example, oriented this way and this, that, but maybe this one could be oriented vertically.
Is there
This.
any pros and cons? Which is there?
So actually, the immediately next slide, I explore different designs, and so we have some results that actually show that this is actually the best design. So thanks. So yeah, so this is as Yasu proposed. There's actually many different designs that are possible, and so we actually show different types of designs with the different lenticular arrays, and we denote the orientation by the direction of these green arrows. So they might vary in the direction of the orientation, which are kind of these first three. And they can also they can change by how large the individual lenticular arrays are. And we even include a design that would be very difficult to make because these are many small lenticular arrays. So what we're actually going to do is in simulation, we're going to test to see which design is the best. And in the simulation, what it does is it orients and positions a virtual calibration object in a scene many different times and produces the image measurements of that configuration that we can use for pose estimation to see which design is actually better. So here we show the results. In this experiment, we actually measure the sensitivity of each design to noise in the hue measurement that's used to optimize for the rotation and focal length. So we show the rotation and the focal length estimates first. Sorry, and I also need to mention that this simulator doesn't have the manufacturing error that I introduced before, and so we can use all the pixels as measurements to optimize for the rotation and focal length. So here we show the rotation estimates, and we show the error for the X, Y, and Z axes independently. And in this plot, we define the rotation error as the angular difference between the known direction of the local axes of the calibration object and the estimated direction. So from these results, we can see that actually most of the designs do pretty well, except this design B. And so if you look at it, with this design, you have the two different oriented lenticular arrays, which aren't actually perpendicularly oriented. So what this means is because they're not orthogonally oriented, that it doesn't give very strong rotation constraints. It's along the cylinder. Yeah. Right. And so if we look at the focal length estimation, it's a slightly different story. So here in the magenta, we show the known focal length, but the design C through G have a fairly good performance. However, design C performs a little bit better. And so, actually, Yasu, in your question, I believe design A is the reciprocal per se of the design in C. And from this example, we can see that that design performs worse than the C, which is the best. And so, this design is the one that's based on the physical prototype that I've actually been showing already in this chapter. And the reason it performs well is that these lenticular rays are as far away as possible from each other, and so this gives very strong focal length, very strong constraints on the focal length. So that was a simulated experiment. Now I show a physical empirical experiment where we actually tried to do the camera calibration using a physical prototype of the calibration object. Yeah, absolutely.
Explain briefly why C is the best.
C is the best, right. So if you're imagining that you're trying to calibrate the camera, if you have rays viewing the calibration object that are very different, you would get much stronger constraints than they would be if they were very similar. And so in this case, the design has the lenticular rays separated such that it creates this widest viewing angle possible of the calibration object. Does that make sense?
So you have a certain amount of budget for creating these lenticular arrays. Why don't you just forget about the middle part and take the top and bottom, maybe put 2 more columns on the sides. And if your goal is to maximize the angle difference,
So for sure, it's important to have at least 2 different orientations. In order to properly constrain the rotation, you need those 2 different orientations. So maybe if you have one that's far away in this direction, and then this one it's actually in the vertical direction, I'm not sure that you would still get those strong constraints. Oh, I see. So just make it empty in the middle? Yeah, you could do that. And then you could do stuff like put different symbols so then you can recognize to an image or whatever. Yeah,
well, when you're putting a virtual object in front of it too, it gives you a blanker background instead of having colors moving on.
Like a little frame. Cool. Turns out these are really cheap to make. They're like pieces of plastic, and so one of the great additional benefits of this method is it's fairly easy to do it because you can create these lenticular rays by just ordering online blank lenticular rays and using your color printer in your home to create the pattern. All great questions. So now I wanted to switch gears a little bit and look at the physical prototype. So in this experiment, what we're doing is we're taking this calibration object and we're rotating it around a single axis in front of the camera. And so in this experiment, I just wanted to mention that the local reference frame of this object is such that the z-axis is the surface normal. But then when we look at translation results, the z-axis is actually the depth between the calibration object and the camera. So here we show rotation results with this prototype where we compare this initial optimization and then the refinement optimization on the right. First, I'll focus on the initial results where we show the per frame rotation error as defined, similar to with the simulation experiments. And then we show the summary statistics on the bottom, and this is for each axis. What we can see is that with this initial optimization, we can get errors below 3 degrees, but we do see a striking difference between the results for the z-axis as compared to the x and y-axis. And the reason we have this is because our calibration object gives very strong constraints for rotations around the x and y axis. And it's these measurements that actually define the z-axis. So that's why it's so much lower. If there are any errors in the estimation for rotations around the z-axis, then it would manifest as the direction of the x and y axis. So now we can compare this initial estimation.
Why do the errors in x and y oscillate like that?
Like here up and down per frame. It's a good question. I'm not quite sure. We're not modeling things like noise and the color measurements or things like that. But the variance is about a degree. So there could be things happening like there could be glare off the lights that looks slightly different that reflects off the plastic of the lenticular ray. That might be one of the reasons.
So the question, for question is that systematic or is that
So you're saying it's an error, but there can be a systematic component.
Right. And actually what I'm not showing is we've actually created methods to try to deal with these potential types of challenges that deal with trying to measure color accurately. So actually in the pose estimation work, for example, we do things like we incorporate a color balancing parameter in the optimization to be able to try to compensate or mitigate any sort of effects. So now I wanted to compare the initial estimation results versus those of the refinement. With the refinement, we can see is the error is much lower, and in fact we get rid of this discrepancy between the X and Y and Z axis accuracy results. And this is because in this optimization we're actually deriving positional constraints from the points of the corners of the lenticular array. And so these point correspondences actually give very strong constraints on the rotation around the Z-axis. So this works very nicely with our lenticular arrays, which give very strong constraints around the X and Y axes. So in the same physical experiment, I'll now show the focal length and translation error results. So with the focal length on the left, we can see with the refinement similar to before, the results improve to have a median of about 5 degrees of error. For the translation estimation results, we see almost 0 error for the X and Y direction of the components of the translation. But we do see some error in the Z component, which again is the depth or the distance between the object and the camera. So there is ambiguity between the focal length of a camera and an image and the distance of an object in that image as well. So that means that any errors that might show up in the focal length estimation will propagate and show up as error in the translation. So that's the reason why we see more in the Z-axis. It's worth noting that this median error is about 18 millimeters, which is only about 2% of the distance of the between the calibration object in the camera. So it's still quite good. So as before here, now I show more qualitative results, where I show how the calibration object performs for a variety of different cameras in different focal lengths. So as before, I show the input image with the rotation estimation visualized as the direction of the axes, and I show the known and the estimated focal length, as well as the percent error in the title. So at the top, we show images from cell phone cameras. This is an iPhone S5, I believe, and this is a Samsung Galaxy S6. And then the middle and the bottom rows are from an SLR camera at a variety of different focal lengths. So with the very close focal lengths, we see very good focal length estimation results, and still good results for medium focal length cameras. But we do see a slightly more error in focal length estimation for the longer focal lengths, which are more challenging. Overall, though, the rotation estimates are pretty spot on for these calibration objects. So with our camera calibration method, it's now possible to create augmented reality applications that aren't possible previously, specifically when the input video has a varying zoom. So here we show an augmented reality application where we composite this digital and not to scale Earth and Moon as if it were actually in the scene, specifically right in front of this calibration object. And because our camera calibration method allows us to estimate the focal length of the camera or the zoom of the focal length in every image, then we can make it look realistic even though the camera is zooming. Here we'll go ahead and show it. So as the person moves and reorients the calibration object, you can see that the model moves along with it accurately. And through the different zooming, again, because we can optimize the focal length, we can accurately resize the model so that it has a believable perspective. It's worth looking at again. There's too much time spent on this tonight, I guess.
Is there a reason there's a plant in the back?
Yeah. So the plant is to show that it's still easy to find this object automatically in an image, because these plants are challenging because they have a lot of different colors and different geometries. So because we have these very saturated colors, it's actually really easy to find it in an image, even in this like challenging environment.
So the lenticular array is automatically found.
Yeah.
You don't
No. Good. So that's the end of this section. Are there any questions that remain for how we do camera calibration with these colorful lenticular arrays? Yeah.
Do you take into account distortion of lenses, especially at
We do not. So the pinhole camera that we use to model this is a simple linear function, and so it's not able to do that. In reality, the typical models, which have like a radial distortion coefficient that is more as you get to the outside, even in that case, there's not a lot of distortion that might cause a lot of problems for this method.
So in this video, the focal length changed. And that's how we knew that the thing should be resized. What if the focal length didn't change? Just the camera was moved in the resized?
The camera moves.
Or the combination of camera location movement and the zoom that keeps the angle difference on that film the same.
Yeah, so the way that this object projects into the image is also dependent on the depth. And so if the translation estimate we get from the object is such that the object is farther away, then it would also be smaller.
And you also have the depth measurement.
Correct. So it's the full pose, which is the orientation of the calibration object, as well as the translation, so what the position is, and then the focal length per image. Any remaining questions, Abby? No?
On the background question, would it be more challenging if the background has moving objects or shifting lights?
As long as the objects weren't other lenticular arrays, I think it would be fine. Or something that's, so in this method, I mean, to be honest, it's not like a major contribution how we find this automatically, but the way that we do it is just by looking, for example, for a very, very saturated object, which it turns out most things in the world are not really saturated. The wall, the white wall isn't, this blue isn't very saturated. So it's a very good cue to find things automatically. Okay, great, awesome. So now that we've gone over how we use large colorful lenticular arrays for camera calibration, I wanted to spend the last section on describing how we create new types of fiducial markers using lens-lit arrays. And these fiducial markers actually create black and white appearances for cues for orientation instead of the color that we saw for the lenticular array. And so the reason that we're trying to avoid color now is that it turns out it's actually kind of challenging to measure color accurately. So here we have a scene where a camera is looking at a calibration object and producing some image of it. And so measuring the color accurately is challenging because it'll depend on like how bright the scene is, what color the light is. It'll even depend on what the physical process that is happening on the actual imaging sensor that samples the light in the scene, as well as any sort of pre-processing that the camera might do before we even have access to the data. So because we don't really know how these things work and that they have different effects, it makes it very difficult to measure color accurately. So to ground this, I wanted to show a really interesting example where, in this case, this shows that visual sensors have trouble measuring color. In this case, the visual sensor is the human eye. And so, judging from the reaction, I think a lot of people recognize this image, which was made very famous on the internet last year. But this is the interactive session, so I wanted to see if anyone would recommend what two colors this dress is. Gold and white. Does anyone else see blue and black? Right. So it made popular because it turns out that there's kind of an even split between whether people see it as gold and white or black and blue, which this is maybe not as convincingly gold and white for me in this picture. But the reason that it's ambiguous is because this has really terrible lighting, and because the lighting is ambiguous, the colors actually look different for different people. Actually, turns out that the real color is black and blue. So, bummer for some people. But,
Maybe the biggest contribution of this.
yeah. Right. Do you remember one thing? So, to address those challenges in measuring color accurately, we kind of abandoned this colorful cues that we get from for example, the camera calibration object, and we created a new type of fiducial marker that has black and white appearances. So we use lenslets arrays to create this marker that has orientation-specific black and white appearances, and it's able to do this just like the lenticular array, where it focuses parallel rays of light using each optical element onto a pattern on the back. In this case, instead of using strips of Roy G. Biv pattern, we actually just use a pattern that consists of randomly placed black dots onto a white background. And so the result is this video, this here on the right, where we rotate by 1 degree each frame. So as you can see, for different viewpoints, the lenslet array has different black and white appearances. So here we show a canonical form of one of those viewpoints to make it easier to see. So with this lenslet array, we're able to encode orientation with the black and white appearances. What's interesting about this marker is that the appearances of each individual lenslet actually change independently. And so to get constraints, we actually measure the grayscale value at the center of each lenslet. So because we measure each lenslet, we get a constraint for each lenslet of the lenticular array, and it means that in a single image, we can derive many constraints. Sure.
2 out of these 4 are very ambiguous in terms of the sampling value.
Right. Right, so it's a certain amount of sampling. However, it turns out that in this case, where it's kind of transitioning between black and white, it actually carries a ton of information, because in contrast, if it were all the same color and you had very many different views of the same color, there's not a lot of information. But in contrast, if you notice that the lenslet is changing appearance at that viewpoint, then you know you have much stronger constraints to what orientation the lenslet is.
Why don't you use, for example, percentage rather than just a single sample count?
So across the entire lenslet, or
That one thing, for example.
the whole lenslet array?
Not the whole lenslet array.
Yeah, so actually we're getting to a point where we're trying to get away from actually measuring a grayscale value, and what we actually do is we end up taking a discrete measurement of whether it's just black and white. And so we do this to kind of try to avoid the same type of challenges that we have for the color measurement, if that makes sense.
If you're sampling more than just a single pixel, sampling.
Yeah, it's a very small neighborhood. I mean, 5 pixels or something. But I want you to hang up on that number, but it's a small neighborhood. It's not the whole thing. And the reason we do this as well is because actually for different viewpoints, when you warp into this canonical view form, they'll actually, because you're seeing a 3D spherical object at different angles, it almost looks like the lenslet is moving around in this canonical view. So if you sample the center, you know that it's always going to be at the very top of the lenslet array. So you're always sampling from the same point. If that makes sense.
I lost this part. So
Yeah.
I think that dot kind of bit magnification is under this whole thing.
Right.
This thing is under that thing or under individual lens.
Yeah, so this whole pattern is under this whole section. And so one lenslet might see a dozen black dots or something like that. Yeah. However, because it's random, each lenslet will see a different pattern of black dots.
Why not? I thought that if you follow a similar style, which we did in the past, the point is about just making color to grayscale, put the same small pattern under individual lenslet, repeat, that was one thing.
Mm-hmm.
That's a natural way is to every single spherical thing, you put the pattern.
Yeah.
You should see the same pattern over the whole thing. That's not a kind of similar thing.
Yeah, so you could design it such that, for example, like if you just put stripes, it would have the same type of orientation-specific appearances. And then the entire lenslet would have the same appearance or similar appearance. As we saw before, you would probably end up having to calibrate each individual lenslet anyways, because it's very hard to mount it and create it. But actually, as we'll see later, it's pretty interesting that each lenslet, because it has a different appearance, it gives kind of a weak constraint on the relative orientation. But when you use all of them together, you get a very strong set of constraints to estimate the viewpoint. But there have been other work, like the lenslet array, that uses like 2 different types of colors so that you can encode the 2 different orientations with color. But we're trying to get away with that because it's difficult to measure color accurately. In the dissertation document, we actually use like different stripes that are kind of similar to the lenticular array. That's based on the discrete cosine transform. So maybe that's you can look into that to get more details about using those types of patterns. Okay, so for this fiducial marker, we're using the measurements for each individual lenslet. And so to be able to derive constraints about these observations, we have to calibrate what the appearance of each lenslet is for a given set of viewpoints. So to do that, we look at this lenslet array for a dome of viewpoints, which are 30 degrees from frontal parallel. And we look at granularity of 2 degrees. In order to do this, we have an automated system that has 2 rotation motors that positions the lenslet array in front of the camera to have this orientation. So we take exactly 677 images in order to cover this whole viewpoint, all these different viewpoints. And so now I'll talk about how we actually encode viewpoint using the appearances of each lenslet. So with our calibration method, what we're doing is we look for a variety of different viewpoints, what the measurement, the grayscale value is at the center of this lenslet. And a way to visualize that is with this response map, which shows the grayscale value for rotations around the y and the x axis. And so because, as I mentioned earlier, that each lenslet actually has a different random text pattern underneath it, these response maps will actually be unique per lenslet array. Per lenslet. And what we do is we actually take this response map and we threshold each grayscale value for each viewpoint to exist in some state, which we show here on the right, which is called the state map. So you could do this for a variety of different states. You choose 3 or 4 or whatever. But in this talk, we focus on using 2. Yeah. Yeah, so this is just like a jet colorization of the grayscale value. So of one lenslet, and this is for a set of viewpoints. Yeah, so when we discretize, then that's how it turns this grayscale value into a black or white measurement, because we set a threshold at gray, and then on one side is white and one side is black. That makes sense. So the reason we do this discretization is that with 2 states, instead of having to worry about, like, is this the right grayscale value, is it within 5 grayscale values, it's just a matter of, is the pixel black or white, which is much easier to measure. So it's interesting to think about how much information a lenslet might encode. With 2 states for a single viewpoint, it might carry a bit of information. And so if we consider all the measurements of all lenslets for a given viewpoint, you could represent that as a bit string. And here we show a few arbitrary examples of bit strings. In a perfect encoding, you would be able to create, if you had n lenslets, you'd be able to create 2 to the n different bit strings, unique bit strings, which means that you could uniquely encode 2 to the n different viewpoints, which is pretty exciting, because if you consider the set of viewpoints that we calibrated the lenslet array, you would be able to encode all the viewpoints uniquely with only 12 lenslets. However, in reality, it's really difficult to design and manufacturing a lenslet array that has this precise ideal encoding. However, we can look at...
That was 12 because you then oversampled it, right? Because you said 677 different viewpoints.
Yeah.
But then then you oversample for more viewpoints later? Is that why it's long? 677 should be able to be.
Yeah. So there might be. So I end up upsampling this. Yeah. So I end up upsampling to like close to half degree of precision. So we might not be able to design this lenslet array to have this perfect property, but we can characterize and try to measure how close our Fisher marker actually comes to that. So here shows some examples of state maps per lenslet array. For some lenslets, the pattern underneath it will be all one color, so either all black or all white, and so it'll have very low entropy. However, other lenslets will have this diversity, or will be closer to a 50-50 split between the black dots and the white background behind it, and so it'll have very high entropy. But what's interesting is that if you look at all the lenslets, it ends up having an average entropy of 0.8, which for two states, the maximum entropy would be 1. And so it shows that even though we're just using a pattern that has these randomly placed black dots, we actually get fairly close to an optimal, this ideal optimal encoding. So now imagine that we have all the appearances calibrated for each lenslet for all the set of viewpoints. Now what we can do is we can use this information to actually infer the viewpoint given a test image where you don't actually know the viewpoint. So in this image, you might sample the center of each lenslet and decide which state it's in, and we represent that this state string here at the bottom, where it shows the state, whether 0 or 1, for a set of lenslets. So in order to infer the viewpoint, we use a very simple voting method. So I'll go over that voting method now. So for a lenslet, we consider the state map of that lenslet. Then what we say is that for all the viewpoints of this, for all the viewpoints of the state map that are in the same state as was measured in the test image, so it's the ones that are red here, we give those viewpoints 1 vote. Right? And so what we're going to do is that with each lenslet, we're going to add a little bit more information from these weak constraints. So if here now we're in a 5th lenslet, we would do the same thing. We consider the state map for all the viewpoints that have the same state as was measured in the test image. We give another vote. And so here I've kind of skipped ahead because I've considered the voting for 5 different lenslets. What you can see is that there are already a set of viewpoints that are getting more votes than the other ones. So what this means is that these viewpoints are consistent with the observations of the 5 lenslets beforehand. So this is just 5 lenslets. If we were to consider more, we keep doing this voting, adding more votes for viewpoints. And pretty soon what we come up with is that there are only a few viewpoints, hopefully, that have many votes. And in fact, we only have 1 that has the most votes, which is very convenient, of course. So in order to actually estimate the viewpoint, what we do is that we return this viewpoint as the most likely viewpoint. Again, I wanted to reiterate, to me it's interesting that each lenslet itself kind of has weak constraints, but as you use more and more of them, you become more confident in an answer, and you get stronger constraints to infer the true viewpoint. However, this viewpoint doesn't encode the full pose of the object. So you only know the direction from the camera to the lenslet array. You don't actually know how it's oriented in space or how far away it is from you. So to do that, we use a nonlinear optimization that minimizes the reprojection error of the 3 reference points that we use to warp the image. We parameterize the rotation by 3 parameters, and because we've estimated the viewpoint, we already know 2 of them, so we just need to optimize for 1 of the parameters. And so in this optimization, we optimize for both the rotation and the translation. So now we'll get to the section where we show some of the viewpoint estimation results. What we did in this experiment, and so this is with a physical prototype. So with our automated system, what we did is we positioned the lenslet array to 100 different viewpoints that are randomly chosen, but are actually different from the ones we used for calibration. And so, what we're looking at in this plot is looking at the viewpoint estimation error in degrees as a function of the number of lenslets that are randomly chosen to do viewpoint estimation. So even with just 20 lenslets out of a maximum 90, we see pretty low viewpoint estimation of less than a degree of error. And if you were to use all of them, you would get to about a quarter degree of median error. Here we show a similar experiment where we're positioning the lenslet array in random orientations, but in this case we use 3 different lighting environments in the room. So on the left we show results from an environment where it's just overhead lights, like in this room. And then we also show results from an environment where, in addition to that, we have a spotlight that shines directly at the lenslet array. And then finally, we use a very extreme environment, which is just 2 direct spotlights directly at the lenslet array that are just pure blue. So the lights are off, and it's only blue light in the scene. So even with this crazy lighting environment, we still get fairly low error in estimating viewpoint. And this is, again, because we're just measuring these discrete black and white appearances of the lenslet array. If we were to take our calibration object, for example, and put it in here, it would be very challenging to actually measure the true hue of the lenslet array in order to get the proper rotation constraints to get good results like this. So that was in estimating the viewpoint, but now we show results where we actually estimate the entire pose. So this is the full rotation and translation of the fiducial marker relative to the camera. And we actually compare using our lenslet array, so the information of the black and white appearances here, versus traditional methods which would just use the 4 corners, the 4 points on this marker. So in this experiment, kind of similar to that with the calibration object, we place it in front of the camera and we rotate around the vertical axis. And we show the error per frame across the x-axis here, and we summarize the median error per axis, rotation axis, in the title. So the top we show the results for the traditional fiducial marker, whereas the bottom is the results for our lenslet array fiducial marker. So for our method, we see consistently low error of under 1 degree, and the median error being about half a degree and this is full rotation estimation. In contrast with the traditional methods, we see pretty high error, especially around this frontoparallel view. So that's what's pictured here, where it looks, the array is perpendicular to the camera. So the closer we get to that viewpoint, the higher the error is. Here we show next I show the translation estimation results. And this time with the plots I put results from both methods on the same plot. So at the top is the results for the x and the y axes. For both methods, these are pretty similar. For the z estimation, we see some differences. So because the origin of this marker is here in the top left corner, that means as you rotate it, you expect a difference in the translation as well. In fact, you would see a linear difference as it gets closer or farther away from you as you rotate it. And so what we see is that our method, the lenslet, the red line here, shows that, albeit a little bit of noise in the translation estimation. However, the traditional fiducial markers, although linear for very obtuse angles, has some perturbations for this frontoparallel positions as before. And so that would suggest that there is error in those estimations. So for the final experiment for this section and for the talk, I wanted to compare our lenslet array fiducial marker against all the different fiducial markers that use microlenses, so whether it's the lenticular array or the lenslet array. So we compare against our chroma-coded markers as well as the lentimark and array mark. And so we report the rotation estimation error in terms of degrees. And we report our results in these columns, and we report the results, we show the results reported by the respective papers of the lentimark and array mark, where they do a very similar experiment where they're taking their fiducial marker and rotate it around the single axis. So from these results, we can see that our lenslet array does better at rotation estimation than most of the markers. The only exception is maybe the lentimark for the x-axis, where it's slightly worse. But this goes to show that these orientation cues that we get from just the black and white appearances are very useful and get really great results. So that's the concluding slide of this presentation, where I used microlens arrays for geometric inference. I covered how we encoded color using lenticular arrays, as well as how we use small versions of those as chroma-coded markers for pose estimation. After, we used large versions in order to enable camera calibration, and then we created new types of fiducial markers from lenslet arrays that encode orientation with black and white appearances. So in our dissertation, we explored these visual cues that give orientation information directly instead of just position constraints. And it's interesting to think about what other types of physical states might be directly measurable with visual cues. For example, could you design some fiducial marker that actually gives you measurements about the physical strain or stress that the object is undergoing, or what the movement is of the object at a single time point? There's actually been some research recently on materials that might make this possible. So on the top, we show some photonic gels that actually change color depending on the mechanical pressure. And at the bottom, we show materials that have gold nanoparticle chains that change color to record the peak pressure put on these polymers. Still yet, there's another material that's actually created from microscopic pillars that, as they change and bend, actually change the optical properties of the material. So these various new materials might give the opportunity to capture even more useful information from a physical state of the object with a fiducial marker. And so it'd be interesting to see how you might better be able to understand the world by using these more generalized fiducial markers. So here I list briefly the 5 publications which presented my research before today at various conferences. And I refer you to the document to look at more details. But that concludes the talk, my talk of how we used microlens arrays for geometric inference. I certainly appreciate any other questions or comments that you guys might have. Thanks.
So this will be the opportunity for mostly people not in the committee if they have questions to ask Ian.
Everything. Covered everything. Great. Perfect. No more discussion on the dress.
How about your tie? Is that a lenslet array background right there?
It's not. No, it should have been. Should have been. That would be pretty cool.
Alright, so I have a question from Austin Abrams, who's at Google, who's the one Skyping in here. Who can see the question. So I will read it as written. So, calibrating for the hue response function in the lab conveniently factors away printing processes, camera response, the hue of the light, room that you're in, etc. What would it take to get around this step so I could download an AR app onto one of many different phones, use a marker you sloppily puts together on a crappy Mohawk printer, and have it work at a rate?
Interesting. Very cool. Okay, so
which nuisance factor would be the trickiest? So that's the question.
Interesting. Okay, so the question from Austin Abrams via YouTube live stream was, there is a calibration process for the colorful lenticular arrays. That's, in our case, we use laboratory equipment, which makes it easier, but how can we just have an end user be able to take these lenticular markers to electronic raves for some reason or another? So that's a good point. So the method definitely depends on this this relationship. There's actually, you might be able to actually optimize for this relationship at the same time that you actually optimize for the pose of the object. So you might be able to do that by having more than one marker, many different markers, and by rotating it in front of the camera in a similar way that Structure for Motion tries to figure out the 3D geometry of a scene using many different images of a scene with cameras that you have no idea what their parameters are. So it seems possible, and actually we have an undergrad working on this technique to try to figure out how we might be able to do that. Another rave questions. That's good, it's memorable.
So I don't have another rave question, but Austin has a different question. I think this was as the black and white markers started. He writes, all right, So camera response and light hue isn't a problem with the lens idea. But maybe it's still hard to line up the lens with the printed paper.
Yeah, so that's definitely true. And as we talked, sorry to repeat the question for the microphone. So calibrating, so it might be difficult to create these black and white appearances with a lens array because of how you might have to mount this pattern onto the back of the lens array. And so with our method, we kind of say, okay, let's not worry so much about it. Let's just calibrate after the fact as much as possible what the final appearance actually is. So it's similar to the calibration object or the chroma-coded markers where you need to calibrate what that relationship is between the appearance and the angle before you use it for geometric inference. I don't think there are any other questions.
All right, let's thank Ian again. I will now invite the non-committee members to speak with us. Yeah. Cool. Always about the announcement. The ones that
All our stuff is just good, so
no.
two